This week we're going to study similar polygons. And the objectives of this class, it will be to identify similar polygons and to use similar triangles. And here we have a definition of similar figures. Two figures are similar if they have the same shape but not necessarily the same size. And here we have a formal definition of similar polygons. When there is a correspondence between two polygons such that, let's look at the figure to the right, the corresponding angles are congruent. So we can see in the figure to the right that the angle A, it is congruent with the angle E. The angle B, it is congruent with the angle F. The angle C, it is congruent with the angle G. The angle D is congruent with the angle H. The length of corresponding sides are proportional. So we're going to make this idea clear. When something it is proportional, or when the length of corresponding sides are proportional, we can see from the figures that one seems like the reduction of the other one, or one it seems like we make that figure bigger than the other one. So any way that you see it, I think that you can see clearly that, for example, the side AB corresponds to the side EF. And since they are proportional, this is supposed to be equals, for example, to the ratio of the side BC and the side FG that are corresponding sides. Then also we can see that the side CD and GH are also corresponding, so the ratio of them, CD over GH, is equal to the previous ratios. And we're missing one more. DA corresponds to HE and is equals to the previous ratios. So this is the meaning of length of corresponding sides are proportional. And then, if these two things happens, if the corresponding angles are congruent and the length of corresponding sides are proportional, or in other words equal, then the two polygons are going to be similar polygons. And we can say that the figure or the quadrilateral ABCD is similar to the quadrilateral EFGH. And here we have the symbol that you can see that when you see it, it is read similar to. So we can say by looking at the symbol, ABCD is similar to EFGH. Let's make an example where we can apply what we just saw. In this example, we're going to compare similar polygons, and we're going to decide whether the figures at the right are similar or not. If they are similar, in case they are similar, we're going to write a similarity statement. So let's see the first question that we need to answer. Are corresponding angles congruent? So let's look at the figure at the right. I notice that I have two figures that both of them are quadrilaterals, and I notice that the angle W is congruent with the angle P. How do I know it? Because they have only one arc, an identical marking for both. The angle W is congruent with the angle P. Same happens with the angle X and Q, double arc, meaning that both of them are congruent. Then I notice that at angle Y and angle R is a little square, meaning that both of them are congruent, and that specifically each one of them measures 90 degrees. And also I notice that the angle Z has 3 arcs and the angle S has 3 arcs. So all the angles in here that are corresponding are congruent. So yes, the corresponding angles of WX, Y, X and PQRS are congruent. And the second question that we need to answer is the following. Are length of corresponding sides proportional? So let's start seeing what is going on. Let me begin with the length of WX and PQ. These sides are corresponding. The WX and PQ are corresponding sides. And the length, so I can write the statement WX over PQ. And the length of WX is 15 and the length of PQ is 10. So we write 15 over 10. And this, if we simplify it, is equals 3/2. So the ratio WX over PQ equals 3/2. Let's see what happens with the other ones, with the other sides that we're gonna find a ratio to compare with and see the value that we have at the end. And I continue with the figures, and I notice that also x, y, and q are corresponding. And so I can write a proportion, a ratio, x, y over q r, and I notice that x, y is 6 units and q r is 4 units. So if I simplify this, 6 over 4, this becomes equals 3/2. So the ratio x, y over q r is equals 3/2. So we already have two ratios whose answer is equals to 3/2. Let's see if we can continue. We need to find 4 ratios. Why 4 ratios? Because we have figures with 4 sides. So let's continue with the corresponding sides. Let's compare the corresponding sides. So after x, y, and q r, we're going to continue with y, z, and r, s. So y, c over r, s, it will be equals, the length of y, s is 9, and the length of r, s is 6. And 9 over 6 in lowest terms is 3/2. So we have another ratio that is equals 3/2. So we're missing only one ratio. And the next ratio will be for zw, the length is 12, and sp, that is 8. So zw over sp is equals 12 over 8, and if we simplify 12 over 8, it will be equals 3/2. So we can see that every single ratio that we wrote and we simplify, the simplification becomes equals 3/2. So our length of corresponding sides proportional or equal? Yes, the corresponding sides are proportional. Therefore, the two polygons that we have here are similar polygons, and we conclude that the polygon or the quadrilateral WXYZ, it is similar to the quadrilateral PQRS. Notice that to write this similarity statement, we need to take care of the corresponding vertices of the corresponding angles. W corresponds to P because they measure the same. X corresponds to Q because they measure the same. You can look at the figure, the markings. Y corresponds to R, and Z corresponds to S. So we need to be careful when writing the similarity statement, the same that we did previously when we saw congruent figures. So we have to be careful in the way that we list the corresponding angles or the corresponding. Let's make a second example where we need to compare similar polygons. And again, we need to decide whether the figures are similar. If they are similar, we're going to write a similarity statement. So as before, we're going to answer the question, are corresponding angles congruent? And I see the figure, and it seems like the angle N corresponds to angle P, the angle M corresponds to the angle R, and the angle A corresponds to the angle Q. And I notice that only at the angle N and the angle P I have a marking indicating that the angles N and P are congruent, and there is no other marking. So are corresponding angles congruent? The answer is no. Only one pair of congruent angles are being shown in the figure. Second question, are length of corresponding sides proportional? So let's see. It seems like the side LM is corresponding with the side QP. And let's see the ratios of the sides. 10.5 is the length of segment LM, and for QP the length is 4 units. And 10.5 over 4, 10.5 over 4, if we use a calculator and we divide, you're allowed to do that, the answer that we get is 2.625, and that would be the ratio of the two sides. Let's see if we find the other sides that are corresponding and we get equals to this value. So also I notice that the side MN is corresponding to the side PR. So the length of the segment MN is 18 units and PR is 12. So we get the ratio 18 over 12. That if you simplify it and reduce it to lowest terms, it will be 3/2. And if we simplify like a decimal, we get 1.5. That is different from the previous value that we get. And let's see now the ratio of the sides NL and RQ. NL is 12 units, the measure of the segment. RQ is 12. RQ is 9, sorry. And we get 12 over 9. And 12 over 9 is 4/3 in lowest terms. And if we divide to get a decimal, it would be 1.3. As you can see, none of the ratios are equal. So our length of corresponding sides proportional, or if we want to say it in that way, equal? And the answer is no, the corresponding sides are not proportional. Therefore, the two polygons are not similar polygons. None of the two conditions serve. And to two polygons to be called similar polygons, both of these conditions, so corresponding angles must be congruent and corresponding sides must be proportional, are not followed. And each one of them, if we want two polygons to be similar, both of these conditions must be true. Two polygons are not similar polygons. Let's make a new example. We're going to apply similar polygons, and in this case we have given that the quadrilateral ABDC, it is similar to the quadrilateral RPSQ. And what we need to do here is to find the length of the segment AC. So in the step 1, we're going to write a proportion, and what we're going to do is to guarantee that the corresponding sides match. So let's see. Remember that I need to find the length of AC, so it will be one of the, when we write a proportion, guys, and a proportion is the equality between two ratios. So what I need actually is two ratios, and I'm going to get these ratios by comparing corresponding sides. So I notice, let me begin with AC. AC corresponds to RQ, and AC is the one that we need to find in RQ. Later on we're going to need it. It is 14. So this will be equal, so these ratios are going to be proportional, so they must be equal to the corresponding sides. I need, in the next that I'm going to write, I need to know both length, because in a proportion I have 4 values, and out of the 4 values I need to know 3 to solve the proportion. I'm going to relate it with the ratio AB and RP. So this will be equals to AB over RP. And in the next step, we're going to solve it. Like I mentioned before, AB I know that is 9 and RP is 18. So in the step 2, we're going to replace the values that we just mentioned with the length from the original exercise, or from the exercise that are given, the quadrilaterals. So what we get, guys, is the following. AC over RQ measures 14 units equals to the ratio, the length of the ratio AB, that is 9 units, over the length of the RP, that is 18. So we get the proportion AC over 14 equals 9 over 18. And in the next step, what we need to do is to solve this proportion. So how do we solve proportions? One of the principles, or one of the ways to solve a proportion, is to multiply across. And when we multiply across the proportion in 2, it will becomes 18 AC equals 9 times 14. And finally, to complete the exercise, what I need to do is to leave alone the AC, and what I need to do is to divide both sides by AC. So AC becomes equals 9 times 14 divided by 18. At this point, you can use a calculator. If you can avoid to use it, excellent. I noticed the following to avoid to use a calculator at this point. 9 at the top and 18 at the bottom are both divisible by 9. 9 divided by 9, it will be 1 at the top, 18 it will be 2. So we left 14 over 2, and 14 divided by 2 is 7. So the length of the segment AC is 7. And that would be the value that we were looking for, the length of the segment AC. Okay, here I'm going to leave you to work alone. You're going to find, using exactly the same figure, the same figure, same values, but did you notice in the first figure, in the quadrilateral ABC, not only AC was missing, it was also missing, or is missing, the length of CD and BD. So by using exactly the same procedure as was done before, but with different values, of course, you're going to be able to find CD and BD. So try to do it on your own, so you can find the values of CD and BD. Let's make a new example. In this example, we have quadrilateral ABCD similar to the quadrilateral EFGH, and what we need to do is to find the values for X, Y, and Z. So we can proceed finding any of these values, but in this case, let's begin finding the value of the X. And I notice that the value of the X is the one that corresponds to the segment EH, and the segment EH, it is this is side EH corresponds, and the other polygon that we have in here, to the side AD. So we're gonna begin writing a proportion using the names of the sides. And when we write a proportion, we need 4 sides. So I already mentioned 2 sides, EH over AD. EH corresponds to AD, but also I need to find another pair of corresponding sides, so we can write a ratio. And the size that we choose in this case, that we have chosen, is EF, that corresponds to AB. When we write a proportion, guys, we need to guarantee that out of the 4 values involving the proportion, we know 3, so we can find the other one. So in step 2, what we're going to do is to substitute the values. We need to substitute values. One of them is unknown, and the other ones must be known. So what are the values that we get? EH is X is the value that we're looking for. AD, I look at the figure, and AD measures 15. Then I have EF, and I notice that EF on my figure is 10 over the length of AB, that is 20. Then I have this proportion, and I need to solve the proportion. It could be by cross multiplying. So if we cross multiply, we will get 20 times x equals 15 times 10, or, and then leaving alone the x, so we divide by 20, both sides. Or if you want, you can go directly, and we can leave alone the x, because x is being divided by 15, and the 15 passes to the other side. It will be multiplying times 10, and multiply the 10, and then divide by 20. It will be 150 divided by 20. In lowest terms, it will be 15 halves, or like a decimal, x equals 7.5. So this procedure we use, we're going to use it to find the other values. So let's find now, for example, the value of the y. And I notice that y is on the bigger figure, is DC. Y is represented by the segment, is the length of the segment DC. We need to find the value of the y. And this side DC corresponds to G, let me see, DC to HG. So this ratio, I'm going to need it in here. So I need the ratio of corresponding sides, DC over HG, and I need to choose 2 sides from which I know the length of those 2 sides. And the sides that we're using in this case are AB, that is 20, and EF. So we get the ratio, the proportion is the quality between 2 ratios, DC over HG and AB over EF. So in the next step, like before, we're going to substitute the values. DC is the value that we're looking for, is y. HG, it is 5, equals to the ratio formed by AB, that is 20, over the length of EF, that is 10. So we got a ratio, the equation between 2 ratios, a proportion, and what we to do again is to multiply across. So to solve the proportion. And again, if you notice, if you leave alone the y, is multiplying, is dividing, passes multiplying, so it will be y equals 20 times 5 divided by 100. So the value of the y is equals 10. We repeat exactly the process, this process that we have been using to find y to find c. And I notice that for find c, if c is the length of the segment FG, and FG corresponds to BC. So I need a ratio FG over BC. One of those is unknown, so the other ratio that I need to use, I need to know the length of both sides. So in this case, we're going to use the length of the sides EF and AB that are corresponding sides. So in the next step, we replace the values. FG is unknown, is Z. BC, it is 30. EF is 10. AB is 20. Again, we multiply across, or we just leave the Z alone. If 30 is dividing, passes to a side multiplying, and if we solve it, the value of the Z will be 15. And here we have the values of X, Y, and Z as we wanted since the beginning to find. So here we have, guys, an idea that is connected with similar figures, and it's the idea of dilations and scale factor. A dilation is a transformation that changes the size of an object. So if we can make an object looks larger or bigger than actually it is, we're making a dilation. The transformation is called a dilation. Or if we have a figure that is really small, and for any meaning we can make it bigger to look a figure that is bigger, we can enlarge the figure. This is called also a dilation. So a dilation is a transformation that changes the size of an object. And also connected with this is the idea of the scale factor, that connected with similar figures, is the ratio of the length of the corresponding size of 2 similar polygons. it indicates the relative size of a polygon or one polygon compared with another one. So that's two ideas that we need to have clear. In this example, we're going to find the scale factor. So let's see the example. We have these triangles ABC and ZYX that are similar. So AB, for example, corresponds to CY, AC corresponds to CX, and BC corresponds to YX. So we have these figures. And what I need to do is to find the scale factor from A to triangle, and what we're going to write in here, guys, is the other triangle that is similar to, respecting the other. So ABC is similar to the triangle CYX. And the scale factor, it's found like this. So since we are making it from ABC to CYX, we're going to begin with one side of the triangle ABC. So let's see, for example, AB, what is the, let's choose AB and CY. So let me write the ratio of AB, that is 18, and CY. CY, that is 9. So 18 over 9, it would be the scale factor. So I compare two corresponding sides, and the answer that we get of this ratio, it would be the answer. So it would be, I repeat, AB, I can choose that one, over CY. And 18 divided by 9, it would be 2. And if you want to choose any other pair of sides, corresponding size, and the ratio must be the same, and this will be the scale factor. Also, somebody may say, let's use AC. AC, it is, let me see, AC is 14, and CX is 7. So 14 divided by 7, it will be 2. And you want to make another one, the other ratio, the two ratios that we can compare would be BC and YX. BC, it is 10, and YX is 5. 10 over 5, it will be 2. So the scale factor of ABC to CYX is 2. And we have it here. Now, we can reverse this. We can find the scale factor from the triangle CYX to the triangle ABC. And as you can figure it out, what is going to happen is that the answer of this is going to be the reciprocal of the answer that we get. So let's see. What it would be, let me choose one side. One side from the triangle CYX and one corresponding side of the triangle ABC. So let's choose, for example, CY. And I notice that CY, we begin with the triangle at the right. CY is 9, and AB is 18. So 9 over 18, it will be, in lowest terms, it will be 1/2. So we divide both sides by 9. And we get 1/2. And this is going to happen the same if you compare the other corresponding sides. So the answer would be 1/2. So as you can notice, it's the answer that we get a reciprocal of the other one. And what is the meaning behind this? If we see that the scale factor from ABC to triangle CYX is 2, the triangle ABC is twice as big as the triangle CYX. And the scale factor from triangle CYX to ABC, we can see that the triangle CYX is 1/2 the measure of the measure of the ABC, the size of the triangle ABC. So that's the difference. It's the difference between seeing the scale factor from one figure to another one. So in one is 2 and the other one is 1/2, like in this case. If in one is 4 and the other one, it would be 1/4. So this is the example, one example, or to give a meaning of the scale factor. Let's make a new example of the scale factor. In this case, we have this figure to the right, and what is represented in this figure is the following. There is a rectangular patio around a pool, and this is similar to the pool. And what we need to do here is two things. Calculate the scale factor of the patio to the pool, and find the perimeter of both. So in here we have the following, guys. Since the patio and the pool are similar rectangles, we can use the scale factor comparing the length of both the patio and a swimming pool or the width of the patio in the swimming pool. So we compare the length of both the patio and the swimming pool. It would be 48 feet compared with 32 feet. So this notation that we're using here is a column notation, 48 feet column, 32 feet. That is exactly, or it is equivalent to write 48 feet over 32 feet. Or using the other dimensions of the width, 24 feet over 16 feet. In this case, you use 48 over 32 or 24 over 16, the answer at the end, it would be 3 halves. You can use your calculators if you want. 48 feet divided by 32 feet, the units feet and feet cancel. It would be 48 over 32. Both of them are divisible by 16. 48 divided by 16 is 3, and 32 divided by 16 is 2, so it would be 3 halves. And the same is going to happen if you have 24 feet over 16 feet. 24 feet over, like a fraction, 16 feet, the units cancel, the feet are gone. And 24 over 16, I notice that both of them are divisible by 8. 24 divided by 8 is 3, and 16 divided by 8 would be 2. So at the end, the scale factor will be 3 over 2, or 3 colon 2, or 3. That is exactly the same idea. And what about the perimeter? The perimeter, it is the sum of all the sides of the figure that we have. So the perimeter of the patio, since this is a rectangle, we have from previous knowledge that in a rectangle we have two pairs of opposite sides that are going to be congruent. We know that they are parallel, but in this case we need that they are congruent. So we add twice 24, so 24 plus 24, or 2 times 24, plus 48 plus 48, or 2 times 48. So this would be equals 144 feet. And the same happens with the perimeter of the pool. It will be 16 plus 16 plus 32 plus 32, or twice 16 plus twice 32, and the answer will be 96 feet. And let's see the last example of this lesson. And in this example, we're going to write proportionality statements. In the diagram, the triangle BTW, it is similar to the triangle ETC. And what we need to do in A is to write the statement of proportionality. So, in here, we have the following. I see that the side ET, it is corresponding to the side BT of this triangle, of these two triangles. And I need to find three ratios of corresponding sides. Also, I notice that this must be equal, because the triangles are similar, to the ratio formed by the sides TC and TW. So we already have two pairs of corresponding sides, and we need to find a third pair of sides. And the third pair of sides that are corresponding are CE and WB. So these two sides make up a ratio. And these three ratios, since the triangles are similar, must be equal. So this is the statement of proportionality. In B, we're going to find the measure of the angle TEC. And I notice that the measure of the angle TEC, or the angle TEC, corresponds to the angle TBW, or just with the angle B. And since they are corresponding angles, and the two triangles are similar, these two angles measure the same. Therefore, since the angle B, it is congruent with the angle TEC, the measure of the angle TEC is equals 79 degrees. And in C, we're going to find the length of the segment ET and BE. To find ET, we're going to write the following ratio. We're going to write the following proportion. So we need two ratios. And I notice that in this figure, I'm going to use information, since I'm going to need to write a proportion, I need to get 4 values, which one of them must be the unknown. And the unknown, don't forget, is ET. So I see that the ratio of the size, or the corresponding size, CE and WB, I can use those because I know both values, must be equals to the ratio that contains the information that we need to find, ET. And the side ET corresponds to BT in the triangle that we have here in the triangles. So if we replace the values, what we get is the following. CE, it measures 3 units. WB, that it corresponds to EC, measures 12. And the other ratio, ET, that is the value that we need to find, corresponds to TB or BT, and BT is 20. So to solve this, we use cross multiplication, or we just leave alone the ET. It passes multiplying the other side. 3 times 20 divided by 12, so the value that ET is 5 units. And finally, to find the measure of BE, I noticed that in one of the sides of this triangle, I look at the BT, the length of that side. It is clearly indicated that it's 20, and we just found that ET is equals to 5 units. So to find the measure of the angle of the segment BE, what we can do is to find the difference between the length of BT and ET. So BE becomes equals to the length of the segment BT minus the length of the segment ET. So in other words, BE is equals 20 minus 5, and 20 minus 5 equals 15. So the measure of the segment BE is 15 units. And this is all. Thank you for your attention, and I hope that this is everything is clear in this section. And if you have any questions, that you bring all your questions to our next meeting. Thank you again for your attention, guys.